Hello students, welcome back to another physics lesson. In today's class, we will be learning about work, energy, and power. These are very important topics in physics and they are frequently tested in WAEC, NECO, and JAMB examinations. By the end of this lesson, you should be able to define work, energy, and power, state their formulas, identify their SI units, and solve simple calculations. So, let's get started with the first concept, work. What is work? In physics, work is said to be done when a force applied to an object causes the object to move through a distance in the direction of the applied force. This means that simply applying a force is not enough. The object must actually move. If there is no movement or displacement, then no work has been done. Let's look at some examples. Suppose a student pushes a table across the classroom. Since the table moves in the direction of the applied force, work is done. Now imagine a boy pushing against a wall. Even though he is applying force, the wall does not move. Since there is no displacement, no work is done. Here's another example. A man carries a load on his head while walking on a level road. He applies an upward force to support the load, but the load moves horizontally. Since the force and the movement are in different directions, no mechanical work is done by that upward force. From these examples, we can conclude that two conditions must be satisfied before work is said to be done. First, a force must act on the object. Second, the object must move through a distance in the direction of that force. The work done by a constant force is equal to the product of the force and the displacement in the direction of the force. The formula is work done equals force times distance, where W equals work done measured in joules, J. F equals force measured in newtons, N. D equals displacement measured in meters, M. If the force acts at an angle theta to the direction of motion, then we use W equals force times distance cos theta. The SI unit of work is the joule, written as J. 1 joule is defined as the work done when a force of 1 Newton moves an object through a distance of 1 meter in the direction of the force. Therefore, 1 joules equal to 1 Newton meter. Now, let's solve an example. Worked example. A horizontal force of 50 Newton acts on an object and moves it through a distance of 6 meters in the direction of the force. Calculate the work done. Solution. Given, force equals 50 Newton, displacement equals 6 meters. Using the formula, W equals force times distance. Substitute the values into the formula. W equals 50 times 6. W equals 300 joules. Answer. The work done is 300 joules. Now that we've understood work, let's move to the next concept. What is energy? Energy is the capacity or ability to do work. Every activity that involves movement, heating, lighting, sound production, or the operation of machines requires energy. Before we look at the different forms of energy, let's learn an important law in physics. The law of conservation of energy states that energy can neither be created nor destroyed, but it can only be transformed from one form to another. This simply means that the total amount of energy remains constant, even though it may change from one form to another. For example, in an electric bulb, electrical energy is converted into light and heat energy. In a moving vehicle, chemical energy stored in fuel is converted into mechanical energy. In a hydroelectric power station, the potential energy of water is converted into electrical energy. Energy exists in different forms. Some of the common forms of energy include mechanical energy, kinetic energy, potential energy, heat or thermal energy, electrical energy, chemical energy, light or radiant energy, sound energy, nuclear energy, magnetic energy. Among these forms, kinetic energy and potential energy are the most commonly studied in mechanics. Let's begin with kinetic energy. Kinetic energy is the energy possessed by a body because of its motion. Any object that is moving has kinetic energy. The faster the object moves or the greater its mass, the greater its kinetic energy. Examples include a moving car, a rolling football, a flying bird, flowing water. The formula for kinetic energy is kinetic energy equal to half mass times velocity square, where K is the kinetic energy in joules, M is the mass in kilograms, V is the velocity in meters per second. Worked example. A body of mass 4 kg moves with a velocity of 5 meters per second. Calculate its kinetic energy. Solution. Given mass equal to 4 kg, velocity equal to 5 meters per second. Using the formula, kinetic energy equal to half mass times velocity square. Substitute the values. Kinetic energy equal to 1 over 2 times 4 times 5 square. Kinetic energy equal to 50 joules. Therefore, the kinetic energy of the body is 50 joules. Now let's look at potential energy. Potential energy is the energy possessed by a body because of its position or configuration. A body raised above the ground possesses gravitational potential energy because work has been done against gravity. Examples include water stored in an overhead tank, a stone held above the ground, a book placed on a shelf, a stretched rubber band. The formula for gravitational potential energy is potential energy equal to mass times acceleration due to gravity times height, where P is the potential energy in joules, M is the mass in kilograms, G is the acceleration due to gravity, approximately 10 meters per second square, H is the height above the ground in meters. Worked example. A body of mass 6 kilograms is lifted to a height of 4 meters above the ground. Taking G equals 10 meters per second square, calculate its potential energy. Solution. Given mass is 6 kilograms, height is 4 m, acceleration due to gravity is 10 meters per second square. Using the formula, potential energy equal to mass times acceleration due to gravity times height. Substitute the values. Potential energy equals 6 times 10 times 4. Potential energy equal 240 joules. Therefore, the potential energy of the body is 240 joules. The SI unit of energy is the joule, J. Finally, let's move to power. Power is the rate at which work is done or energy is transferred. In simple terms, power tells us how quickly work is done. Power is a scalar quantity because it has magnitude only and no direction. The formula for power is power equal to work done over time, where P is the power in watts, W is the work done in joules, T is the time in seconds. Since work and energy have the same unit, power can also be written as power equal to energy over time. The SI unit of power is the watt, W. 1 watt means 1 joule of work done in 1 second. Therefore, 1 watt equal to 1 joules per second. Worked example. A machine does 900 joules of work in 15 seconds. Calculate its power. Solution. Given work done is 900 joules. Time taken is 15 seconds. Using the formula, power equal to work done over time. Substitute the values. Power equal to 900 over 15. Power equal to 60 watts. Therefore, the power developed by the machine is 60 watts. Thank you for watching. If you found this lesson helpful, don't forget to like this video, subscribe to the channel, and turn on the notification button so you never miss our next physics lesson. See you in the next class.